The informative path planning problem requires one to find sensing paths for robots while accounting for their total flight time so that the collected data results in an accurate data field reconstruction. This problem is particularly prevalent in environment monitoring. The informative path planning problem can be viewed as a sensor placement problem with path constraints. Most prior work focused on selecting the sensing locations that maximized mutual information. Mutual information is computed by first discretizing the environment and then building a covariance matrix amongst the discretized locations. Then the matrix is inverted to compute mutual information, but this matrix inversion operation is cubic in the number of discretized locations. Computing mutual information requires this costly operation to be performed from scratch for every given set of sensing locations. Additionally, for accurate mutual information estimation, a finer discretization is necessary, which can significantly increase the computational cost. Sparse Gaussian processes are computationally cheaper approximations to Gaussian processes. They reduce the compute cost of GPs by leveraging inducing points, which can be interpreted as the control points that determine how the learned function behaves. These inducing points are optimized so that they are strategically placed amongst the training data points, and their labels are computed from the training set. The method allows us to make test set predictions using only these inducing points, which substantially reduces the method's computational cost. We specifically employ the variational free energy-based sparse Gaussian process. The method's objective function is shown here. The k-terms represent covariance matrices, with the subscript n denoting the training set points and the subscript m indicating the inducing points used for covariance computation. This objective function has 4 key components. The first term is just a constant, so we can ignore it. The second term determines how well we predict the labels of the training set. Now what happens if we ignore the data fit term? What remains are the complexity term, which ensures that the inducing points are well distributed, and the trace term, which ensures that we capture the correlations in the whole training set. Note that this function depends only on inducing point locations and the kernel hyperparameters. Given the kernel hyperparameters, we can optimize this objective function in an unsupervised manner to get the solution inducing points. We leveraged this insight to formulate the sensor placement problem using SGPs. We start with an environment. In this case, it is a 2D environment. We randomly sample and label points in the space, which will be used by our SGP as its training set. After that, we initialize our inducing points at random locations and build the covariance matrices to compute the objective function. Using the known kernel hyperparameters, we can then optimize the modified SGP objective function without the data fit term to get our solution inducing points, which correspond to our solution sensing locations in the environment. In this paper, we generalized our SGP-based sensor placement method to address the informative path planning problem. We achieved this by initially setting up an SGP similar to our approach in the sensor placement problem. Next, we sample random unlabeled points and initialize the inducing points. Now here is the key difference. We used a traveling salesperson problem solver to find an initial path that visits all the sensing locations. Furthermore, we update the SGP's objective function to include a distance penalty term, which calculates the total distance of the current path and penalizes the objective if the total path length exceeds the distance budget. Subsequently, we optimize this SGP, incorporating the distance budget term to obtain the solution path. Moreover, we extend our method to handle multi-robot scenarios by introducing additional inducing points and employing a vehicle routing problem solver to get the initial paths, and then optimize the SGP with a separate distance budget term for each robot. Our method does not rely on mutual information, and unlike black box optimizers, we employ gradient descent to optimize the inducing points. This leads to significantly faster convergence times. We can model continuous sensing robots by interpolating additional inducing points along the path that traverses the existing inducing points. These additional points represent the information gathered along the path. However, incorporating these additional points increases the cost of matrix inversion. To address this challenge, we aggregate the covariances corresponding to the interpolated inducing points. This step reduces the size of the covariance matrix that requires inversion while still accounting for the information along the path. During optimization, using gradient descent, we compute the gradients with respect to all the inducing points, including the interpolated points, and then backpropagate the information from the interpolated points to the original inducing points shown in red. This strategy enables us to optimize only the original inducing points while effectively modeling continuous sensing robots. We can also use the same trick to model non-point sensing robots. Here is our method for informative path planning with 4 robots, each with a distance budget of 50. Finally, we demonstrate our approach for a single robot, such as a drone. We model it so that the area sensed by the drone varies based on its height from the ground. We see that our method optimized the robot's height at each sensing location to ensure full coverage of the environment